Welcome to Bednik Tutors YouTube channel. In this channel, we will be breaking down topics of each science subject in order for you to have a better understanding of each topics. Because as a teacher, we believe that every student should understand fully every topics they are being taught. So, in order not to miss out on any of our videos, because all the videos we'll be uploading are very important, please do well to subscribe to our YouTube channel. Also, like and share. We also have a Telegram channel where you can communicate with us, ask us questions, and meet with other educators. The link of our Telegram channel is in our YouTube bio and comment section. Now, say these after me. I understand mathematics. I understand physics. I understand chemistry. I understand further math. That is a spirit. Bednik Tutors. Excellence is our word.
Good morning, class. So we'll be running a practical on WAEC 2020 on electricity. So our major work is we'll arrange all the apparatus. So we'll be able to know how it is being run. Then later along the line, we'll do the reading corrections on the board. So I just want you to follow us as we proceed. It's very simple. So we'll still be starting with the electricity first. That was WAEC 2020. WAEC 2020 electricity. So journey with us as we go. So just as we continue, we'll be looking at this the diagram for WAEC 2022. So we'll be looking at the way the diagram is. We have the ammeter. This is the ammeter. This is the ammeter. We can see the reading of the ammeter from 0 to 3 ampere. And if we are dealing, you see the negative here, you see the positive here. This is also another positive. This is 3 ampere, this is 15 ampere from 0 to 3. If I place my DC cable here now, it will read from the upper one from 0 to 3. But if I place the positive, my DC cable on this positive side here, it will read the lower part. But I'll be dealing with 3 ampere because of the measure of my voltage. My voltage is just 3.0 volt, which is 1.5 plus 1.5. It's connected in series. Then that's that for the ammeter. You know ammeter majorly. We use ammeter for measuring current, DC current. Then we have the resistance. This is the resistor here. Is used for measuring resistance. This is 1 ohm. This is a standard resistor. It's not a variable resistor. And we have what we call a resistance bus. This is a variable resistor. You realize that here you have 1 ohm. If I'm putting this on 1 ohm here, you see times 1. That's on 1 ohm. If I'm told to calculate 2 ohm, it will be 2, 3. Then you realize that later I may be told to find, maybe I have a measurement that deal with like 60 ohms. I will just place this on 6. The other ones will be on 0. This one I will adjust it to be on 0 so that it does not have effect on it. Because resistance bus is a conglomeration of various type of resistors that are connected in series. So you see 0 here, you see 0 here, you see 0 here. I put it on the reset of 0. So it will not be another load on this particular resistance bus. So this is 60 ohms now. If I place it on 3, it will indicate 30 ohms there because it's times 10. So I can take it back to 0. If you look at here, this is 0 here. If I take this times 100, if I place it on 1 now, it will be 100 ohms. If I place it on 2, it will be 200 ohms. The same way, maybe I'm dealing with an higher resistor that involves like 1000. If I place it on here, this will be 1000. I place it on here, it will be 2000. I place it on here, it will be 3000. So I will still initialize everything back to 0. That's that about the resistance bus. So it's a variable resistor. It's not a standard resistor. The same way it does the same work like a normal rheostat 2. Rheostat 2, we have variable resistor, that is 2 or 3 resistors or as many resistors that can easily help us moderate the flow of current within the circuit. Then this is your key, just like the signal key at home. 2 key, you have entrance to your building. Here too, 2 key, we can control the flow of the current. This is the plug of the key. If I move this plug, then automatically, no matter the connection I have, be it in series or in parallel, automatically the flow, there won't be a flow of current. So it will be the one that will judge if there will be flow of current or not. through it, it can show me that, oh, if I insert the plug, the current will flow. If I did not insert the plug, the current will not flow across. So those are the way we know. And most times, even all the time, when immediately you are done with a particular reading, you remove your plug so that your battery does not run down. It also saves that. Then we have our cell. We call this a battery. The addition of two cells forms a battery. This is a cell, this is another cell. This positive side here, this blue part here is the positive side. We refer to this as positive terminal. Then this side here that look like a plain cover of an aluminum sheet is what we refer to as the negative terminal. It's negative terminal. This is a super quality battery. So each of it is 1.5 volt. And theoretically, you know that when you add two cells together in series, definitely the voltage will increase. That is, the potential difference will increase. It's only in parallel that we'll find equality of it. So this is 1.5 volt, this is another 1.5 volt. This is a negative side here. I join it with a positive side here. I've sellotape it, that's why you didn't know. But later, by the time we do further experiment, I will ensure that you see all this. Then this is the negative terminal. And as a senior secondary school student, even up to your university level, you must be able to do your simple electricity connection. Very simple, as a good scientist in the education world. So let's look at our voltmeter. Voltmeter, we have our voltmeter. We use it to measure voltage from 0 to 3. This from 0 to 3. So we have our ammeter, we have our voltmeter. Ammeter, voltmeter. So that is that. Then take note of something. We have polarity. We have the polarity of the cell, polarity of the ammeter, and the polarity of the voltmeter. The polarity is referring to the negative and the positive terminal, the negative and the positive terminal. So there are things we'll be considering in our diagram. So let's start from there now. Let's look at this. Let's look at this. If you have your key here, you see we have the positive cell here, positive cell. This is the positive terminal. We join with the key. So I'm going to bring this. I'm going to bring this here to join with my key, with my resistance bus, then with my ammeter, you can see my ammeter, then with my resistor. So we can see that from that angle there. Then you take note of something very simple. So very simple. You realize that I'm going to join the positive terminal with the key here. It doesn't have polarity. So I'm going to bring any of the cable. I can bring any of the cable. Any of the cable here. I'm joining like this. I want you to see my work. See the way I'm joining like this. I will first of all place the cable, the DC cable, so that you can see. Then I'm joining, please. I'm joining from the key to the resistance box. You can see from here, the other side of my key here. I'm joining with the resistance box here. The other side, I'm joining the resistance box there. You can see here, I'm joining with my resistance box. I join to this. Then, after joining to this, then the resistance box does not have polarity. It has no positive or negative. And mind you, when you are dealing with DC cable, you don't bother if it is a black or yellow cable. It doesn't matter because they are DC. When you are dealing with alternative currents where you handle electricity, AC, voltage, normal household wiring, you'll be conscious of the red, you'll be conscious of the black, which is for your neutral. Your red will be for live, and your black will be for your neutral. Then you also have your green or yellow for your head. As an engineer, that will be stated if later we are teaching undergraduate students for that later in future. We will also access that during our YouTube channel in future. Then you connect here. So we pick another cable. If you see from our diagram, we're connecting to a positive terminal of the ammeter. So I'm going to pick here. Look at here. I will join with the positive terminal here. Just follow the diagram, because in science and engineering we believe diagram is very important. You don't do anything outside the diagram. That's the difference between you and someone who is not educated, who is doing anything in the engineering or science field. So here you see connected to this side. Then the negative side will now be connected back to the positive to the standard resistor here. So this is the negative on the black here. We'll connect it here. Please, it's smooth. Don't worry, it's smooth. I just want you to have a view of it. Connected here to this side here. After it is connected, we'll now join. We join. After that is joined, we'll now come back here. You realize that This is here. We now bring a positive here. A positive here. We join with a voltmeter there also. We join this with a voltmeter here. This is a voltmeter connected at this side here. So we're joining the negative side that has been joined here. We connect with the positive side of the voltmeter. Can you see now? So here the negative from here is connected where they both meet at the standard resistor here. Then connect here with this here. Then later we now connect back. Later we connect back here, then we connect to the positive side, then we now bring the negative here, join with this, bring the negative here. From the diagram, we are following the diagram, negative here, we now join to this negative, we connect back to the negative here. So we now bring this here and connect here by this. So those are how we'll be doing our work. This is our connection. You can realize from here we connected our positive to the positive terminal here. We connected this to the positive terminal. There's a flow from here to the positive here, flows here. There's also another flow here to the positive. Then it will now still later flow to the positive terminal of our ammeter. So just for you to see direct, just the way we saw it directly from the diagram, yeah, you can see from our diagram here that the positive terminal flows to the resistance bus. Here, this is the edge here. From here, flows to the key here. From the key, it flows to the resistance bus. From the resistance bus, flows to the positive terminal. This is the positive terminal of the ammeter. Can we see now? Despite it is black that is closer to here, we did not place it on black. We place it on the positive because the polarity of this battery must flow along with the polarity of the ammeter. The positive terminal must, the DC wire must be connected to the positive terminal of the ammeter. Can we see the flow like that? Because if you mix it in the place of the polarity, you will see your reading going negatively, inversely, or moving towards the reverse side. But if you get the polarity right, the problem of electricity is solved. So move here to the positive. Then you realize that then from positive it comes out through the negative. So there's a loop here. It's connected out, now connected to the edge of the resistor, of the standard resistor here. You can see here being connected from here, flows here. Then it will now get from here is connected to the positive of the voltmeter. This is the positive of the voltmeter now. The positive here, you can see connected to the edge here. That means this has been fulfilled. That's why in engineering and science generally, we follow diagram. We follow our diagram very well. So after then, we now come back to the negative terminal because all the wiring should come from the cell. So we move here. From here, we join to here to this side. From this side, we connect. This is the negative terminal. Here connect to the resistance bus, which is what we've done here. Then the negative of the voltmeter will also be connected to the edge here. This is where they meet here. From this edge here is also here at the edge here. So through that now we have a perfect connection. I want us, you see our cameraman will be able to move it and show you. So you can see the connection. I have a vivid view of the connection. This is a good scientific lab for experiment. So we will now start our reading. From the diagram, the reading diagram which we will show, we are told to find for WAEC 2020, we are told to find the resistance of 1 ohm first. 1 ohm. So we'll start 1 ohm. I touch my battery like this. I move here. 1 ohm. So starting from here. So we started with 0.3 on our voltmeter here. 0.3. Though the battery has worn down because we've worn it before, but our ammeter is 0.35. 0.35. We can see from there 0.3, here since it's on the middle is 0.25. There's something I want you to note. From here we have 10 calibration line from here to here. We have 10 calibration line from 0 to 1. So this is 0 to 1. This is 10 calibration line. You divide it by 10. So one calibration line will be 1 over 10, that will be 0.1. So from here we have 0.3. So voltage will be 0.3. That's at zero. Yeah, we've not taken any reading. This is at zero. You realize that here is also here. This is 10 volts here. 10 volts is 0.5. So one line will be 0.05. You can see it's on 0. If we multiply 5 by 0.5, that is 0.025. So thank you. We will now move to, we are told to put our resistance bus at 1. So we'll now look at the reading from there. If we place it at 1, we can now say here. So we have still 0.25, 0.3 here, 0.3. So that is that. Then we'll continue like that. We put the resistance bus on 2. Resistance bus on 2. We have something like this. You can see that it's reducing 0.25. Here is also 0.25 here. 0.25 here. It was at 0.3 before. 0.25. Then if we increase this again to 4, you realize that it reduces again. This is 0.22, while this is 0. This is 0.3. So along the line, we discover that both, as we are increasing the resistance bus, both the voltmeter and the ammeter is reducing. Both the voltmeter and the ammeter is reducing. So we look from the diagram we had there. These are resistance, these are our ohm. So your resistance is written in ohms, your ammeter is written in ampere, your voltmeter is written in volt. Although we must not cancel because we like there's some error. So that's why this is still a rough sketch. We are still going to perform a correction on the board where we deal with 1 ohm, 1.00. This is for the resistance. This 2.00, it will be in 2 decimal places. 4.00, 6.00, 8.00, 0.30, 0.25. You realize the trend here. As the resistors are increasing, the electricity is also reducing. So there's no fixed value for real particle. It's only in the alternative to particle that you have real value. But when it comes to real particle, all you just deal with is trend. We call it trend when we are marking physics particle. So here now, they will give us an instruction that as the resistor values of the resistance bus are increasing, both the voltage and the current must reduce. The moment you follow that trend, any secondary school that year in year 2020 have their good grade. Even if your own is starting from 0.60 ampere, another person starting from 0.80, the moment is reducing, you have your mark and nothing will affect your mark. So we follow trend. That means that you follow the real apparatus value. So those are some of the things I want you to take note of there. So along the line, we will still explain the basis of the table, the graph we are going to plot, and many other things. Thank you. God bless you. This is still Benic Tutors. We love you. Thank you for following us. Those who have been following us on further maths, calculus yesterday that my wife uploaded, and many other ones. We appreciate you. Please, we still need more followers, and we beg you in the name of God, don't just download our video. Please try and watch it before you download, so that we too can be able to enjoy what YouTube will be doing for us. Please always watch it. We beg you in the name of God. So my wife sent me to you to beg you, please always watch the video before downloading. So please, God bless you. So subsequently, we'll still continue with the table and the graph. Thank you. Pause.
Yeah.
We have the EMF for the battery at 3.0 volt. Then this is the normal reading table. We have the EMF for the battery at 3.0 volt. Have as ohm, the current as ampere, the voltage as volt. Then let's look at the range of the resistance. Where we place these are the variation of the resistance bus: 1 ohm, 2 ohm, 4 ohm, 6 ohm, 8 ohm. So when we put our resistance bus at 1 ohm, we have 0.30 on our ammeter. On our voltmeter, we have 0.55. 0.55. You can see that later at 2, we have 0.25, 0.50. And the current, as the resistance starts increasing, you see the current going down and the voltage also going down, which obey the Ohm's laws, that the higher the resistance, the lesser the current and the voltage, because the voltage is directly proportional to the current, because we know that voltage is directly proportional to current. So the constant there, the proportionality constant there shows our resistance, which is now Ri. So, and you can divide both sides by half here, whereby we now have I is equal to V over half from Ohm's law. The higher the current, the higher the voltage, provided the resistance is constant. So that illustration is done. So from here now, we want to, before we produce our table, it's not good to you to be looking for this on your graph. It will waste your time. So we'll move to the standard form. We find the standard form of this. We find the standard form of this. Form of this. So yeah, look at my here, my, my current. That will be multiplied by 10 power minus 2. So here will be 30.00. This is my current A. Here, 25.00. That 20.00. 15.00. Then 10.00. Then my voltage. This will be V times 10 power minus 2. I converted it to standard form. 55.00, 50.00, 45.00 to standard form 1 to 35.00, then 25.00. Can you see that? And please don't forget something. When you come to your table like this, you must ensure that your table follows a pattern in such a way that your work are neat, you see the way it is, and it follows the normal trend. That is, as the resistance is increasing, the current and the voltage is also decreasing. So, and your work must be neat. You must indicate this, because on a normal ground now, if I want to mark this as a physics teacher, because we also mark Y, I want to mark this as a physics teacher. This I'm going to mark. This I'm going to mark. Let me show you. This is how we mark in WAEC and NEPO. Here now, the resistance value here is given from the particle. So here is just 1 mark. But these are measured value. Because they are measured value, they can be 2 or 3. But they would have indicated that as the resistance increase, the current and the voltage must reduce. So for you particle, another school may start down from 0.5. Here can be 0.6. As long as it's reducing, they are good to go. So this measured value is always high. This can be 3 marks. It can also be 3 marks. Then the fact that you're able to write the table, there's no mark for this. This is on approximated value. The fact that you're able to write this, you're able to write all the quantities and their units correctly. You have your R, your T rather composite table as 1. We call it composite table, write T as 1. Then you were told to find the EMF of the battery. Further, you put it out there. This is also 1 mark. It must be at least 1 decimal place. This must be at least 2 decimal places. The moment you alter one as maybe 0.1, while others are 0.2 decimal places, and you place this one maybe 0.1, and you place it at 1 decimal place, you cancel this, you lose the full mark here. So you have to be consistent. We are working with 3 decimal places. Ensure you are consistent. That will allow you to have your full observation mark. This is 4, 7, 8, 9. So observation here is 9/9. So that's the major work for the table. And the table carry the highest mark. The graph will be 6 marks coupled with some others. So let's move to the graph. So we'll be analyzing it like this in our subsequent experiment. So that's how we mark in white with NECO with the instruction manual. So we'll come back to our graph. Yes. Our graph with 6 marks, as I've said. I've also highlight how the mark is distributed. So I'm going to focus on these two for our graph. So you see the way it is there. We want to read this out. So that's that for the vertical. We look at the horizontal here. So 10.0, 15.0. So on the vertical, you can see the way we arrange the scale. 0 to 5. 5, we look at the lowest. We must find the lowest there. We must find the highest there. So we make the 10 holes will be 5 units. 0 to 5, 10, 15, 20, like that. The same thing applicable here. The 2 centimeter represent 5 units. Though in physics, we don't have to show that in an obvious way. We don't have to. So let's have our 55, 30. So say the voltage VV times 10 per minus 2. This is I A times 10 to the power minus 2. So 55, 30. Look at 55. We looked at 30. So 55, 30, 50, 25, 50, 25, 10, 25, 50, 25, 20, 45, 20, 45, 20, 20, then 35, 15, 45, 20, then 35, 15, 35, 15, 35, 15, then 25, 10, 35, 25, 10. We have it there. So from there, we can easily look at what can be our follow there. We are picking this, amplify this. The line of best which will cause at least 3. So that's settled.
Yeah.
We use plus so that we can be able to trace our value. We'll be able to trace our value to be accurate. So we have here at the edge from here to here. Yeah, yeah, yeah. Okay. So this is our slope. So our slope will now be vertical 55 minus 15. So that's 55. 5 minus 15. The vertical will be 25 minus 5. That's 25 minus 5 multiplied by 10 by minus 2. So at the end we have 40 over 20. 20. Then this has cancelled each other. And that will be 2.0 voltage per ampere, voltage per ampere, volt per ampere. So that's our slope, and that's all about that. So in our precaution, so part of our precautions, we say I avoided parallax error while taking readings on my voltmeter meter and ammeter to be in past tense. Parallax will be PARALLAS.
like this. I ensured and noted zero error for ammeter and voltmeter. I ensured and noted zero. Everything will be in past tense. It's only in GC we use past participle that would ensure. But here, you can though you have to write to. You can also say ensure tight connections at the terminal of each apparatus. So those are things. Then I also ensure that I remove the plug of the key so that the battery does not run down. So you should know at least four, but you are only to write two. So we want to do the allocation of the marks here. This is your graph. Your examiner will write like this: axis, scale, point, line of best fit. Your axis. This half mark. This half mark. Make it 1. Your scale. The moment you notice that from here to here is 5, 10 is equal. Then you have 5 units in 10 holes. So they will give you half mark. We have the axis, as I said, half mark, making 1. The scale, the 10 holes make 5 units. The 10 holes here make 5 units. So this half mark, why this half mark? Make this 1. If we trace this point and it's correct, the first 3. The moment the first 3 are correct, you write 3 here. So all the 3 points are correct. 3. Then the line of best fit. Provided we have 2 here, the line release 2 here, or he has 1 here or 1 here, then your line of best fit, you have your 1 mark. But if it has 2 here and 1 here, that the line does not cross, you have score 0 here. And you must be able to get the first 3 correct before they give you your line of best fit. Those are the conditions. If you have 2 here, 1 here, 1 here, 2 here, it's correct. Or you have 2 here that the line does not cross, you are still correct. So it must be, the point must be evenly distributed along the line of best fit. So T, the total marks here will be 6 marks. Then your slope, the fact that it touches it here, it touches it here, and you place your angle here, you have half mark. Then you go to your slope right. Here is half mark. Here is half mark. Then here, your rotation here is half mark. So your slope is 2. There's no mark for the final one. Then you go to your precaution right, 1 mark, 1 mark. The precaution is 2/2. Although there are some other theoretical aspects too along the line they ask you. So that's all about physics practical. This engineer Anowe Adebayo under Beneath Tutors. Thank you. God bless you. I'm sure you're able to learn 1 or 2 things. So next week we'll be releasing the mechanics. This is WAEC 2020. We call it coronavirus WAEC 2020. Some of the students that wrote this WAEC now, they are investigating, they're serving presently. So this is WAEC 2020. So we'll be doing the mechanics aspect next week. Thanks and God bless. We will be practical. Thank you. God bless. Love you all.